All right, students, so we're continuing our video series on carbonyl nucleophiles that can attack our carbonyl groups, and the next one would be sulfur-containing nucleophiles. So these are the three nucleophiles that bear a sulfur or several sulfur atoms that we'll be focusing on. Notice that they share commonality with our oxygen nucleophiles. Can you spot the similarities? I hope you can, because ketones and aldehydes will react with thiols, which are sulfur-containing compounds, in virtually the same way that they react with alcohols. So let's observe those mechanisms. The first one, it's going to be acid catalyzed transformation of a ketone using methane thiol. So we saw already acid catalyzed transformation of a ketone or an aldehyde using methanol, using an alcohol. In this case, we're going to use a thiol. A thiol is like an alcohol, except it has an SH group instead of an OH group. So this is methane thiol, and in acidic conditions, it's going to be protonated into its active form in the same way as our acetal mechanism. So you see it has the same 7 steps. We'll just see them all over again and how it's going to result in a different product since we're using a different solvent, methane thiol. So methane thiol in its active form will donate a proton to the carbonyl atom, and the carbonyl atom will now become activated, and this activation will make it into a very good electrophile, a very good positive center to remove that formal charge. So our methane thiol in solution will nucleophilically attack that positive center that we created via the same mechanism that we've seen, and that is the product that we're going to get. So we're going to get this activated methane thiol group now attached to our substrate. And in order to remove that positive formal charge on the methane thiol, we need to have it donate a proton. All right, so now it donates a proton to another methane thiol in solution. So now this methane thiol in solution is activated. And that activated methane thiol was used to form this hemithioacetal. So this is kind of like our thioacetal, right? That has our hydroxyl group and it has an ether group, but this is a thioether, students. This is methyl sulfide. So a hemithioacetal is a derivative of an aldehyde or ketone with a thioether group and a hydroxyl group on the former carbonyl carbon atom. So that's the only difference between a thioacetal and hemithioacetal. Then instead of an ether group, it's a thioether group. So let's continue. We activated our methane thiol, and now that methane thiol is going to be used to protonate our hydroxyl group and convert it into water. So once it's converted into water, it becomes an excellent leaving group, and we're going to have the loss of that leaving group. So water exits the substrate with its electrons, and then one of the lone pairs of the sulfur atom, I hope you all saw, one of the lone pairs will be used to fill that bond that water takes with it. And we learned in the previous video that in order to promote the equilibrium to favor the acetal, we need to remove water from the solution. So we need to distill it out of the solution, and now we just have this activated thioether group. In order to cause this thioether group to become inactivated, we have to nucleophilically attack it once more with another methane thiol group. And that's exactly what will happen. That'll push the formal charge onto the sulfur atom of that methane thiol group, and that can easily be deprotonated by another methane thiol in solution. So in the end, students, I hope you all can see that we get 2 dimethyl sulfides. We get 2 thioether groups, or methyl thiol groups. So we get that. And that is what we call our thioacetal. Same thing as an acetal. Instead of having ether groups, we now have thioether groups that replace our oxygen carbon double bond. So that is what a thioacetal is. And we used it using we created it using a thiol instead of an alcohol. So that was the first reaction I wanted to go over on sulfur nucleophiles. And I'm going kind of quickly because we've already seen this. It's the same mechanism as the other reactions that we saw in the oxygen nucleophiles. So hydrogen sulfide can be used to convert nucleophiles. It can be used as a nucleophile, to convert ketones or aldehydes into geminal diols. So in our last video, we saw that water was used as a nucleophile to convert our ketones or aldehydes into hydrates. And we saw that it only really works on formaldehyde. In this case, we're going to use the analog of water that contains sulfur, this sulfur analog of water, and it's known as hydrogen sulfide, H2S. Hydrogen sulfide will nucleophilically attack our carbonyl groups, and it'll make them into geminal dithiols. So this is a geminal dithiol. It's a carbon single bonded to one thiol group, single bonded to another thiol group. So just like our hydrate, except instead of OH groups, we have SH groups. And in order to accomplish that, we used hydrogen sulfide instead of water. I'm not going to discuss the mechanism by which this happens because your book does not discuss it, but just know that hydrogen sulfide will convert this into a geminal dithiol, similar to our hydrate mechanism. So that was using hydrogen sulfide. The last mechanism that I do want to show you is the mechanism that parallels the nucleophilic attack of ethylene glycol. We're going to use this substrate instead, this sulfur analog of ethylene glycol. This sulfur analog is called EDT, 1,2-ethane dithiol, EDT. EDT can create cyclic acetals just like ethylene glycol can, except it's going to result in a little bit of a different product. And that product is going to have very awesome chemistry that we're going to explore. So let me show you all, once again, the mechanism. It's the same as our ethylene glycol mechanism. Always, we start with protonation to activate our carbonyl group. So EDT will donate one of its protons to our carbonyl group to activate it and create a positive formal charge on the oxygen that will cause the electrons of the double bond to move closer to it, therefore creating a positive center. That positive center can be attacked by another mole of EDT, by one of the lone pairs of the sulfur atom. So the sulfur atom will nucleophilically attack there, and then the pi bond will break, and the bond will move up, or the lone pairs of that bond will move up onto the oxygen, creating a formal charge now on the sulfur. So that sulfur formal charge needs to be removed because sulfur doesn't like to bear positive formal charges, just like oxygen doesn't. So what will happen is that that conjugate base of EDT that we created in the first step will accept that proton from our substrate in order to remove that formal charge. And now, students, you might recognize that we have a thioacetal. So we have our hydroxyl group and our thioether group, our thioacetal. Allow us to continue. We get another protonation of our hydroxyl group to create a water group, and we know that water is going to exit the substrate as an excellent leaving group because of it, leading to the formation of a carbocation that is immediately attacked by this sulfur atom. But before that can happen, we know we need to distill our water. We need to remove it from our solution in order to favor the formation of the cyclic thioacetal. So once again, that lone pair is going to attack here, and that is going to give us, students, our cyclic thioacetal. Except it's still in its activated form. So in order to remove the activated form, we allow our base over here to accept the proton and remove that positive formal charge. So this, my dear students, is a cyclic thioacetal, and we formed it using EDT, ethane dithiol, 1,2-ethane dithiol, from our carbonyl group. Okay, a cyclic thioacetal. So now, if you all understood this, I want you to answer question number 7. I want you to predict the major product that is expected when each of the following compounds is treated with 1,2-ethane dithiol in acidic conditions. So pause the video in order for you to do this, and for extra practice, write the names of the substrates. So students, here are the answers, so you can check your work with that. I include that the answers are within the PowerPoint as well. All right, so why did I go through all this trouble, students? Why do I need to, convert my carbonyl groups to cyclic thioacetals when I can just, convert them to regular cyclic acetals? Well, students, it's that cyclic thioacetals have a very special kind of chemistry. Cyclic thioacetals, students, can undergo what is known as desulfurization. The D prefix should indicate to you that we're taking out. D means without. So without sulfur. We're going to remove the sulfur. And how do we remove the sulfur? When we react our cyclic thioacetal with rainy nickel. By removing that sulfur, that'll convert our cyclic thioacetal into an alkane. Let us see how that is accomplished. So here I have my ketone that was converted into a cyclic thioacetal using EDT. If I react that cyclic thioacetal with rainy nickel, it'll desulfurize our cyclic thioacetal, it'll undergo desulfurization, and it'll convert it into an alkene. An alkane. So those sulfurs are removed and replaced by hydrogens. So that's a way, students, in order to convert our ketones into alkanes. We first make them into cyclic thioacetals using EDT, and then we expose that cyclic thioacetal to rainy nickel, which causes desulfurization and results in the formation of an alkane. So this allows, again, another method for reducing a ketone or aldehyde to the corresponding alkane. We, in acidic conditions, add EDT and then rainy nickel, and that results in the alkane. So if that made sense to you, I hope you can now accomplish transformations using sulfur nucleophiles and that you can answer this question. So predict now the major product that is expected when each of the following substrates, and you can give them their names to practice, is treated with the following reagents. So go ahead and pause the video so you can solve this problem and then check your answer. So these are the answers, students. We saw that they're all converted to the alkanes. All right, so that was our discussion on sulfur nucleophiles. The next video will continue with nitrogen-containing nucleophiles.